Hi, this is Mrs. Barbara. This is AP Physics Mechanics C. Today's topic is weight. The objectives are: note acceleration due to gravity. G is independent of mass m of the body. Understand how the weight of an object changes as it moves away from the Earth's surface and as it moves toward the center of the Earth. What the weight of an object inside a shell in deep space is. Be able to relate the weight of an object to the general expression for gravitational force. Weight and gravitational acceleration. The weight of a body is the total gravitational force exerted on the body by all other bodies in the universe. When a body is near the surface of the Earth, we can neglect all other gravitational forces and consider the weight as just the Earth's gravitational attraction. At the surface of the moon, we can do the same thing. We consider the body's weight to be the gravitational attraction of the moon and so forth. Since weight equals gravitational force, we can set as mg equals gme times m over r squared. From this equation, little m cancels. We can derive the expression for gravitational acceleration. So gravitational acceleration due to gravity is independent of mass m of the body because that little m does not appear in this equation. It is only determined by the mass that's create the gravitational field, such as the mass of the Earth or mass of the moon, and the distance between the body and the center of that object. So the equation also allows us to calculate the mass of the Earth because we can measure G and RE. So if we set this to RE, we can find ME. We can measure G and RE. So ME equals G times RE squared divided by capital G, the gravitational constant. So we can have determine the mass of the Earth, which is 5.98 times 10 to the 24 kilograms. We know weight decreases as you move away from the Earth. So here's the astronauts on Earth's surface have 700 newtons. As the astronaut moves away, his weight or her weight decreases. It's inverse squared law. Okay. As the astronauts who weigh 700 newtons at Earth's surface experience less gravitational attraction when above the surface. So the relevant distance r is from the astronaut to the center of the Earth. This is inverse square law. Journey to the center of the Earth. If an object with mass m travels toward the center of Earth, the gravitational force it experiences actually decreases because only part of the Earth's mass, only this part, is pulling on the mass m, pulling this mass. The other part, this outside layer, does not exert a force on this mass. Okay, as the mass goes toward the center, the gravitational force becomes zero. Assume the density of the Earth is uniform and equals to rho, so this rho equals me over v, mass over volume. And this volume, from this equation, we can figure out the inside, this part, the mass of the Earth of this part equals to the density times volume. Volume of a sphere is 4/3 pi r cubed. This r is the radius of inside part. Fg equals G, mass of the object times the mass of the inside, this part of the Earth, divided by r squared. And mass of that inside, this part of the mass, equals to the density times 4/3 pi r cubed. As you can see, this r squared, r cubed, this part cancels, so you'll only have r here. So the rest is just rearrange this because it's number, I move it outside, times g times the mass of the object times the density of the Earth times pi over 3. So the whole thing, this is basically constant times r. So you can see, if we assume the density of the Earth is uniform, we know the gravity on a particle with mass m inside the Earth is directly proportional to r, the distance from the center of the Earth to the object. So outside is inverse squared, we know. Inside is direct relationship. So that's the graph of inside. So again, outside is inverse squared, inside is directly proportional. So on the surface, though, both equations gives us this expression for the gravitational force on the surface. Density of the Earth actually changes. It's not constant from core to crust. Inside is very high, then it's getting less and less dense, the least dense on the surface. So the line is not actually straight, but we can approximate to be a straight line. Weight inside a shell. So this is weight inside Earth. Inside is proportional to R, outside is inversely proportional to R squared. But what if the object is, the Earth is a shell? If the Earth is a shell, Fg equals to 0 everywhere inside the shell because there is no mass here. So there is no gravity inside the shell. An example 7.4, gravity on Mars. An unmanned lander is sent to the surface of planet Mars, which has a radius Rm equals 3.4 times 10 to the 6 meters and mass Mn equals 6.42 times 10 to the 23 kilograms. The Earth weight of Mars lander is 3,920 newtons. Calculate its weight Fg and acceleration g due to Mars, due to the gravity of Mars. At 6.0 times 10 to the 6 meters above the surface of Mars, B is at the surface of Mars. So let's see, the weight equals to G, mass of the Mars times mass of the Mars lander divided by R squared. We don't know mass of lander, we can figure that out. Using the weight on Earth, we can also figure out this R is from the Mars lander to the center of Mars. So we know the radius of Mars and we know how far it's on the Mars surface. We simply add two together to find that R. So R equals to this two add together equals 9.4 times 10 to the 6 meters. To find mass, we can use W equals mg, so m equals W over g, that's 400 kilograms. So that's the mass. Now we can simply plug the numbers into that equation to figure out Fg, which is 194 newtons. To figure out acceleration, we can use Fg divided by m, and gives us 0.48 meters per second squared. Second question, what is the gravity, the weight of Fg and acceleration, gm, on the surface of Mars? We use the same equation. In this case, this r is just the radius of Mars. So we have 1500 newtons. As you can see, on the surface of Mars, it weighs a lot more than when it moves away above Mars. And similarly, we can find gm on the surface of Mars is 3.7 meters per second squared. So these are inverse squared law. As you move away, both gravity and gravitational acceleration decreases, inverse squared. Another way to find Fg is use the relationship between Fg and r. They are inversely related, so this relationship holds. Fg2 is Fg1 times r1 squared over r2 squared. You also have the same answer. Test your understanding. Rank the following hypothetical planets in order from highest to lowest surface gravity. So gravity is gm times little m over r squared. So what it changes is big M change. That's planet mass change and radius change. So the first one is 2, so it's 2 divided by 2 squared. 2 divided by 2 squared is 1/2. So Fg is 1/2 of that on Earth. The second one is 4 divided by 4 squared. That becomes 1/4. The third one is 4 divided by 2 squared. That's just 1. So Fg is the same as Fg on Earth. 2 squared divided by 4 squared. 2 divided by 4 squared. That's 1/8. So the rank from highest to lowest is 3, 1, 2, 4. 7.2 weight takeaway. So what did we learn here? We learned acceleration due to gravity, g is independent of the mass m of the body. We learned the weight is directly proportional to 1 over r squared, or inverse squared law, outside of the Earth, away from the Earth's surface, but it's directly proportional to r when it's inside Earth. And the weight of the object inside a shell in deep space is 0. And we know weight and the gravitational force are the same thing. Let's look at a couple more examples. A spherical non-rotating planet has a radius r and uniform density ρ throughout its volume. Suppose a narrow tunnel were drilled through the planet along one of its diameters as shown in the figure, in which a small ball of mass m could move freely under the influence of gravity. Let r be the distance of the ball from the center of the planet. What is the magnitude force on the ball at a distance r less than the radius of the planet? So from universal gravitation law, gm_me over r squared, we know me is the density because it's uniform times the volume, and volume is 4/3 pi r cubed, so you can see r squared and r cubed cancels, so you have just r left, and this is the expression for Fg is directly proportional to r. Next one, on the axis below, you need to sketch force on the ball as a function of distance r from the center of the planet. We know from here, inside r, when inside the planet, it's direct related to r. Outside is inverse squared, so it looks like this. Another example, 2 moons of equal mass are in circular orbits around the planet. Moon 1 orbits with radius r and Moon 2 with radius 3r. What is the ratio of magnitude planet's gravitational force to Moon 2 to that on Moon 1? So Moon 2 is further, so we know gravitational force has to be smaller. So it can be either 1/3 or 1/9. But you know force is inverse squared to r related to r, so it has to be 1/9. So this is Fg is inverse squared to r, so Fg on 2 over Fg on 1 is the same as r1 squared over r2 squared. R1 is 1, r2 is 3 times r, so it's 1/9. A newly discovered planet has 3 times the mass and 5 times the radius of Earth. What is the ratio of acceleration due to gravity at the surface of new planet to the acceleration due to gravity on the surface of the Earth? We know this g is proportional to m over r squared. So m is 3 times and r is 5 times. So 3/5 squared, right? So that becomes, this is divide, once over something divide, when you divide a fraction you multiply its reciprocal. MP is 3me, RP is 5re, so it becomes me cancels, re squared and re squared cancels. This is 5 squared times re squared, right? So this becomes 3/5 squared, which is 3/25. The answer is A. And that's it for today. Thanks for watching.